Hello and welcome. I'm Poornima Nayar, and I will be talking about REST, GraphQL and gRPC, a comparison. Thank you for having me at Developer 2021. It's a pleasure to be back. The event has a code of conduct, so please follow the code of conduct for the day and let's make sure that the event is safe and a friendly environment for everyone involved. DDD supports the National Museum of Computing, so please donate to the museum if you can. And thank you to the sponsors for making DDD happen this year again. And if you want to tweet about anything at DDD today, use the hashtag DDD2021, and the Twitter handle is Developer Day. A little bit about myself before I start off. I'm Poornima Nayar. I'm a freelance .NET developer, and I'm speaking to you from Langley in Berkshire, UK. I'm a Microsoft MVP for developer technologies, and I also work a lot with Umbraco CMS, which is a .NET-based open source CMS, and I've been an Umbraco MVP for the past 3 years. Non-work me, I have a 7-year-old daughter who I spend a lot of time with. I spend a lot of time reading, mainly fiction, and I'm also a student of Carnatic music, which is a stream of Indian classical music. And that's my Twitter handle, should you wish to connect with me. I will also be available on the Discord channel, Discord server today, if you want to ask me any questions or have a chat about my topic later on. So REST versus gRPC versus GraphQL, that's a hot point of debate among developers. We see all kinds of debates and tweets happening, but that's not the route I want to take for today. It's not a debate. I haven't worked with all the 3 API patterns to say which one is the best. I'm more closer to the REST/HTTP API world. So what I will be doing today is a comparison of the 3 API patterns. We will look at the basics of each of the API pattern, understand what it takes, or understand the basics which are needed to develop an API in each of these 3 API patterns. And from there, we'll go into comparing the 3 API patterns. First of all, we need a common data context to effectively develop the API and compare them. And today, my talk is based on a very simple user database, with each user having an ID, a name, and a headline. So that is my fictitious user database or the data context for the day. And then we will also discuss how APIs can look like when they are developed for this database. And we'll also then try and see what it will look like if we extend this user database to a fictitious social media platform. Don't worry about the GDPR data privacy, because I'm just using Harry Potter characters as my users for the day. So let's start with gRPC. gRPC is a modern open source high performance remote procedure call framework. So it's a flavor of RPC framework or remote procedure call framework. And what is a remote procedure call? So this is the definition that I have from the internet. A remote procedure call is when a computer program causes a procedure to execute in another space, another address space, which is coded as if it were a normal procedure call without the programmer explicitly coding the details for the remote interaction. So the basic idea is you call, or your client program calls a procedure which is remote, but it is called as if it was a local procedure. So this location transparency is one of the key features of any remote procedure call framework. The system effectively hides where the actual resource is located. So it's very true to its name. It's a remote procedure call. And the key or the fundamental unit of any RPC framework is functions or procedures or subroutines. What you do is call a function on another server as though it was a local function. That is the simplest definition of RPC. Everything happens over the network. So what actually happens during an RPC call? Again, we have a client-server architecture. The client functions calls a client stub. The client stub is nothing but a method which packs or unpacks the parameters that's been given. So the client stub packs the parameters on the client using a method called marshalling. The call then gets forwarded to the RPC runtime on the client, to the RPC runtime on the server, and then it finally hits the server stub. So the server stub unpacks the parameters that is being given through a process called unmarshalling, and then it calls the server functions, which actually executes and then returns back a response the same way the request came in. So this is what happens in an RPC call. Talking specifically about gRPC, we know that it's a flavor of RPC, and it's Google's implementation of RPC. It was initially called Project Stubby and was made open source and called gRPC in March 2015. And from .NET 3.0 onwards, we have .NET Core 3.0 onwards. It's got first-class support within the .NET realm. And gRPC favors contract-based API development, which means that you have a contract defined and then you implement that contract. And gRPC is designed for HTTP2 as well. It takes advantage of many of the features that HTTP2 provides with. And I believe that as of .NET 6 and as of now, there's work in progress to support HTTP3 as well with gRPC. Protocol buffers is one term that we need to understand when it comes to gRPC. So unlike REST or GraphQL, it is JSON, where it is JSON that we get back. gRPC relies on protocol buffers. So this is the main communication mechanism when it comes to gRPC. And it is, again, Google's proprietary open source mechanism to serialize structured data. In fact, if you have worked with something like Google Home, you would come across protocol buffers there too. It is language neutral, platform neutral, as well as extensible. And data in protocol buffer is structured as messages. So if you can see the screen, there is a person reply message there with 3 fields: first name, last name, and a Boolean field. So which means that each message is a record or key value pairs called fields. So it's key value pairs and they are called fields. Every field has a type and a number. This number is particularly important because when data is serialized, it's stored against the number rather than the name of the field, which is one of the reasons protocol buffers are smaller in size as well. And this number is also important when it comes to versioning in gRPC, but that's beyond the scope of the talk. But it is a nice thing to know about. And messages are transmitted in binary format with protocol buffers. So that's about protocol buffers. Another thing that we need to get ourselves familiar with is the proto files. They are files with .proto extension, and that is the contract of the API. This is where the contract of your API is defined. And it has the definition of the gRPC service. Typically, one proto file corresponds to one gRPC service. That's the best practice that is recommended. And each service has a couple of procedures or functions. And what you also have in the proto file is the messages that are sent between the client and the server. This is how a proto file looks like. This is a screenshot from the Visual Studio out of the box template for gRPC projects. We start off with a syntax, which defines the syntax for the proto file, which is proto3 at the moment. We have an optional C# namespace. So with proto files, we have Visual Studio tooling, which helps you generate code, basically C# code. And when C# code is generated, it is put against the namespace that we specify in this file. We also have a package which I have specified, which is completely optional. If we don't have the C# namespace, then it looks for the package greet file and the package name as the namespace. We then have the service definition. So in my case, the service is called greeter. So one proto file equals one service. And my service has just one method or function called say hello, which accepts something called a hello request and returns something called a hello reply. Every procedure or method in a service should have an input or the input message, which is something like hello request. I don't think you can have a method which doesn't accept anything. We also have the messages, which is the request and the responses as a part of the proto file. This is the protocol buffer syntax. Going into a bit more detail, what happens behind the scenes with the Visual Studio tooling for gRPC is that every service that you have in every service in the proto file gets generated as abstract C# classes. And the name of the C# class follows the pattern service name dot service name followed by the word base. So this service generates a class called greeter.greeterBase. And the messages that you have in your proto file gets generated as POCOs with the same name, and the fields are matched up to C# equivalent types for you as well. This happens on the server side. So this is your server side. And to connect to this API on the server side, we need a strongly typed client as well. Again, Visual Studio has tooling for that. And every service can generate a client-side code as well. And again, it follows the format greeter, the service name dot service name client followed by the word client, which means in this case, it would be called greeter.greeter client. And the code generation is controlled by the references in your CSproj files. So if you have a reference to a proto file in your CSproj file, it attaches an attribute called gRPC services, and the value of that attribute controls the code generation. So if it is set to server-side code is generated. When it is set to the client-side code is generated. The default value is both, where you have both server as well as client-side code generated, or it can be set to none if you want a library just of protofiles which you want to share between your server and client projects. So as you might have correctly noticed here, there's a very strong coupling between the client and the server with gRPC APIs. So let's talk about how the methods can look like when it comes to gRPC. So if I want to get the users or get a particular user by the ID, I would have a proto file with some methods in it, say get users, get user by ID. Of course, it accepts an input request and returns a message as well. If I want to create or update or delete user, again, methods or functions which accepts input messages and returns output messages. That's a basic CRUD operation. Now, if you want to extend this and build that fictitious social media platform around the users, again, you would probably have a different proto file with different methods in it. If, say, the user has stories or user can create stories, there would be a get stories for user method. Then you can have a get story by ID method. You can have get top user stories. You can have get story comments, get latest activity of the user, and so on and so forth. So it is very action oriented. Do this, do that, get me this, get me that. So this gRPC is completely based around action-oriented methods. So that is gRPC. When we talk about gRPC, we also need to talk about some of the methods available in gRPC or gRPC modes. Till now, or what we saw is the unary method, where the client can send in a single message in its entirety and the server messages back with a single response in its entirety. gRPC also takes advantage of the nice features with HTTP2, which is the streaming and request multiplexing. So we have a second mode called server streaming, in which the client can send in one request, but the server streams messages back. Then we can have client streaming where the client sends in a stream of messages, but the server responds back with a single message. And then you can also have bidirectional streaming where the client sends in a stream of messages and the server sends back a stream of messages as well, all taking advantage of the HTTP2 features. We can also have metadata with the messages that we send to the API and what the API sends back as well. We have request headers, which we can send into the server. We can have response headers, which can come back from the server. In addition to headers, there's also something called as trailers that is sent back from the server. Especially, it can help when there's server streaming or bidirectional streaming, where the server sends back a stream of messages. Response trailers, unlike the headers, are served after the response is complete. So if you have a stream of messages coming back from the server, this can help to say how many packets of information has been sent back to the client, or if there is an error, what happened, and what is that error all about. These are kind of information that you can have in response trailers. So headers and trailers. Moving on, Some advantages and disadvantages of gRPC. We have lightweight messages with gRPC and we have high performance because of the small size of protocol buffers, and protocol buffers and gRPC in general is more like a specification. It's a standard. So there is less debate between the client and server going on. There's built-in code generation that we get with Visual Studio. We have streaming options, which is kind of very special to gRPC. And in fact, I want to highlight today that every API pattern has some kind of key feature to it, and streaming options are something which are key to gRPC. There's, again, reduced network usage with protocol buffers because of the lightweight nature of it, and gRPC is scalable. However, there is tight coupling between the client and server, which means versioning is in the picture. There's limited browser support because we are still reliant on HTTP2 and some of it is still not out there with the browsers. There's zero discoverability unless and until you document everything up. The proto files can only serve as documentation only up to a certain point, but there is a requirement for documentation with gRPC APIs. And what is the fundamental unit of gRPC? That's functions can go against it as well. You could easily have function explosion with gRPC. And finally, the data that's used to communicate is not in human readable format. It is in binary format. So that's a quick sneak peek at gRPC. And let's move on to REST API, which is probably the most popular and the most adopted API pattern in the world at the moment. REST stands for Representational State Transfer, and it was first presented by Roy Fielding in his famous dissertation in 2000. He suggested REST as an architectural style for distributed hypermedia systems like the internet. With REST, the key or the fundamental unit is resource. Anything that can be represented as a thing in itself is a resource. So it can be a person, it can be a web page, it can be a phone, a car, anything that has a solid representation can be a resource. So what REST says is, here are some resources and here is what you can do with them. REST is all about resource, collection of resources, acting upon those resources, etc. Resource has a unique resource identifier, which is a way to identify a resource. And every resource has a representation as well, which is made up of data, some metadata, and hypermedia links. So every time a programmer talks to a REST API, they are giving a resource representation to the API and getting back a resource representation. And how does it look like? So this is the data and the hypermedia links that form the part of the response the response. And you also have the metadata, which is data about the response in itself. So this is an example of resource representation. Again, when you're sending data in, you are giving some form of representation along with some metadata. REST is driven by 6 constraints. So as long as your system conforms to the 6 constraints, you have a RESTful system in place. So the first one is client server, which means, again, we have a client server architecture with the client asking for information and server sending back information. The system should be stateless, which means that every request that is sent from the client should be complete in itself so that the server can understand and act upon that request. The server should not wait for any request that came before a particular request or after a particular request to fulfill a particular request. And finally, any session management should be on the client, should be never done on the server. Cacheable is another REST constraint. Note that cacheable is the constraint, not caching. So you can mark responses as cacheable, and those responses which are cached at any point between the client and the server can be served or reused for requests that are equivalent in future. Uniform interface, this is probably the most important of the REST constraint, which is driven again by 4 another sub-constraints. So any resource that you take should have a unique way of identifying it, like a URI. You should be able to manipulate resources in multiple formats like JSON or XML or text. However, none of the actual formats or the types are not a REST constraint. It can just be manipulated in different formats. It should be complete in itself, that is self-descriptive. So it should contain all the information that it needs to act upon the resource. And finally, HATIOs, which we will speak about later, which completes the rest. There's layered system as a constraint, which means that RESTful systems can be made up of layers, with each layer talking to one layer above or beneath it. And layer should be pluggable, which means that you can take away a layer or say replace or change it or even add layers. Finally, there's an optional constraint called code on demand, which means that you can even serve up applets as a part of REST constraints. This is my understanding of code on demand constraint. There are some myths when it comes to REST. The first one I want to talk about is REST equals JSON over HTTP. Just because you have JSON over HTTP doesn't mean that you have a REST API. Any RESTful system conforms to the 6 constraints that we spoke about. And just because you serve JSON HTTP, that's not REST, because REST doesn't speak about JSON or HTTP anywhere in its constraints. Another thing that we think is that REST is RESTful procedure calls. This happens, I think, on the course of developing an API. So as developers, we all want to start developing the best REST API, the complete RESTful API that we spoke about, which conforms to all the 6 constraints. But somewhere down the lane, it starts becoming like point to call or invoke methods or invoking method calls over HTTP. Again, not REST. And finally, the biggest myth is REST equals HTTP. That's not the case. REST is an architectural style, and Roy Fielding thought that REST would be really ideal for distributed hypermedia systems like the internet, which ran on HTTP. Again, Roy Fielding was behind REST, and he was also behind the original HTTP RFC, which means that you would see similarities between the two keywords that we have here, but REST is not HTTP. HTTP is a communication protocol, and REST is an architectural style. But Roy Fielding again thought that REST, because it was inspired from internet and he saw it as a way and mean of standardizing internet, he thought it was ideal for systems like internet. But what we have with REST is reusing HTTP. HTTP comes with a very rich toolbox, and REST efficiently reuses that toolbox, like caching, headers, authentication, etc. What we have with any REST API is a root entry point. The idea is that from the root entry point, the users would be then able to navigate the API just like they would navigate a website with a collection of web pages, and each website having a collection of links to figure out what the resources are, how we can act upon the resource, or how we can actually act upon related resources, etc. So for example, this is a screenshot that I have. You start off with the endpoint, go into a certain user, then you can figure out what other actions are available on that particular resource for me. So a REST API should be ideally like a website where you browse a website. That's the exact way you would browse a REST API as well. And how do we start off with REST APIs around our user database? We have a single unique URI for our resource, which is users, and we use HTTP verb to act upon the resources. Again, reusing the HTTP toolkit. So if you want to get the information about a collection of users, which is our resources, or a particular user, which is the resource, we issue HTTP verb, called HTTP get, and we get the response back with a correct status code. If you want to act upon the users and create a user, you would issue the HTTP post verb to this particular URI and pass it a request body, get the response back along with the status code. To update a particular user, you would issue the put HTTP verb. And to delete a user, you would issue the delete HTTP verb. As you can see, we are playing with the HTTP verbs here, but we have a single unique uniform URI for our resource. That is the key of REST. And going further, what about the fictitious social media platform that we have? Would you have something like this? for REST, get stories for user, get story comments, etc. That's not REST. That is again becoming to the or going into the RESTful procedure call world. This is where Hatios comes into the picture. Hatios is considered the REST nirvana. Till now, we have been talking about HTTP APIs and what completes HTTP APIs or what makes HTTP APIs RESTful is HATIOS, which is an acronym for Hypermedia as the engine of application state. So as I said before, RESTful API, you start off with the root entry point and the users come in, browse through the root entry point and try and understand how we can act upon resources, how we can retrieve information about resources, how we can say read or understand what other related resources are there for a particular resource and how to act upon them. So this is the concept of HATIOS, and that is fulfilled by hypermedia links in the response that comes back. So if I'm retrieving a resource like a user with ID 1, of course, I get the name and headline back. But what I also have is a set of hypermedia links which says this is the URL for getting a particular user or retrieving this user. If I want to update this user, again, I have a URL for that. If you want to delete this particular user, then there's a href again for that. And finally, users can have stories. So this is the URL for getting the stories for this particular user. So as you can see, you can read information about the user, how to act upon that particular user or resource, how to even understand related information about the resource. That all comes in from the response. However, there is no standard as of now for HATIOS. HAL or Hypertext Application Language is a work in progress standard convention, and two other types or types have been proposed as well, application HAL XML and application HAL JSON. But again, these are MIME types which are still work in progress, and it's not a standard by any means so far. Pros and cons of REST, we have a decoupled client and server, which means the API can evolve over time. It's scalable, and because of the reuse of HTTP, there's seamless integration to HTTP, and any client which can issue an HTTP request can consume a REST API, which means you have all sorts of clients starting from desktop apps, mobile apps through to websites which consumes REST API. And because it is all reusing HTTP, we have superior browser support as well with REST APIs. However, RESTful APIs can get really chatty. Imagine I want to achieve something like get top user comments or something like that. Then I would have to make multiple API calls before I can gather that information. Remember, not RESTful procedure calls. Going through the single URI per resource way, it can get really, really chatty. REST is not a standard or a spec by any means. It's an architectural style, which means that every developer or teams around the world have their own best practices being followed. You can have big payloads with REST. And of course, we have the overfetching, underfetching, and N+1 problem. Overfetching means I retrieve a lot of data, use a part of it, and discard the rest. And with underfetching, at no point I have all the data that I need. So that's underfetching. So I go fetch more data. So underfetching and overfetching goes hand in hand. And of course, to retrieve information about N resources, I need N+1 calls, which actually paved the way for GraphQL. So GraphQL's very existence was because of these three disadvantages that REST came with. GraphQL was invented by Facebook back in 2013 or 2012, I think, when their first the first mobile app for Facebook was completely panned by the critics for how high the network usage was and how it was draining the battery life. GraphQL is a query language for APIs. So it's very different to REST or gRPC. It's a query language, and it's got a runtime on the server for fulfilling those queries. And it acts upon your existing data. So you have query language, you have a runtime which kind of understands and parses that queries and then gives you the data back. And GraphQL acts on your existing data. When we talk about API patterns, GraphQL comes as one of the cool kids on the block and is probably one of the newer API patterns as well. At its simplest definitions, what we are looking for GraphQL is we have types, say users can be a type, story can be a type, and types have fields. And with GraphQL, what we are doing is asking for specific fields on specific types. Say, for example, I'm saying, hey, get me the ID and name of all the users. So that is how GraphQL is, asking for specific fields on specific type. So if you imagine your data graph, data as a graph, GraphQL extract or helps you extract parts of that data graph. So that's where GraphQL is smart at. What we get with GraphQL is a single smart endpoint. Just like REST, we have a single smart endpoint, but that is only what we have, that single endpoint. You cannot go further than that endpoint, unlike REST. With GraphQL, that endpoint takes in complex queries and builds the data output. Let's see what that means. So in the screenshot that I have, I'm asking for a course with ID 1045 and then telling, get me the fields ID, credits, and title. Yep, that's fine. And then I'm saying that I also want to understand the enrollments against the course, which is like related information. And I'm saying, and for all the enrollments, that is student, I need the first name, email address, and last name of the student. So this is all what I need from my API at the moment. And what I get back is JSON, which absolutely mirrors my query. So if you can see the right-hand side of the screenshot, the data that I get back mirrors the query, and I don't get anything more than I asked for. So exact fetching is another feature of GraphQL. So GraphQL is all about understanding the query that comes in and responding back with a data in the same shape that you ask for, which means that the client is always in control of what they want and what they ask for. And the fundamental unit of GraphQL is query. You ask for data and get data in the same shape. Some of the features of GraphQL, it is strongly typed. It has a strongly typed schema at the heart of every GraphQL API. GraphQL is a specification, which is a standard, which means that across the world, across the different programming languages, we have various implementations of GraphQL. I'm from the .NET realm, so there are two packages or third-party packages or implementations of GraphQL in .NET, which is Hot Chocolate and GraphQL.NET. GraphQL has this nice feature of being introspective, which means it can query itself to understand more about the API. And this has given rise to self-documenting tools. So which means that your API is always up to date as far as the documentation is concerned. Again, GraphQL is hierarchical, which means that if you have a data hierarchy, GraphQL respects that hierarchy. What you get back from GraphQL is a JSON response that mirrors the query. GraphQL is an application layer. It doesn't concern itself with where the data is stored. It is all about understanding queries and giving you back the data that you asked for. So your data can come in from the database, any database. It can come in from a REST API, and even a collection of other GraphQL services. And a single GraphQL endpoint then can then aggregate data from all these services and put forward the data that you asked for. Because the client is in control of what they ask for from the server, GraphQL tends to be version free, which means that if I add a new field to the GraphQL API, as long as the client doesn't use it, it is as good as that field not existing. The only time that you can break the versioning is if you remove a field that is being used or change the nullability. So it is almost fair to call GraphQL as version free because there are ways and means to get around deleting a particular field in GraphQL. Finally, GraphQL is transport layer agnostic, even though HTTP is the most common method of consuming GraphQL APIs. The heart of any GraphQL API is called a GraphQL schema, and across the programming languages, the implementations help you establish the schema in your API. So let's have a look at what schema is made up of. The first thing is object types. So schema can have or should have object types, which is a representation of your object. So in my case, it'll be users, stories, comments, etc. Then you have the operation types in GraphQL. First one is queries, where you read or get information about an object. Mutation, which is an operation type to act upon the object type, say insert, update, or delete the data. And one of the key things that we get with GraphQL is subscriptions, which stands for pushed updates. So we have object types and the operation types, which makes up types in the GraphQL schema. Every GraphQL endpoint out there would have object types and queries as the absolute minimum. Mutations and subscriptions are optional, or you can add it if you want to add it. And types, regardless of whether object types or your queries or mutations, the operation types are made up of fields, with each field having a name, a scalar or a complex type, which is the type of the field or the data type, and the resolvers, so which resolves the field to concrete data. Let's talk about each of the operation type in greater detail. Starting with query, it is one of the operation types in GraphQL and the top level entry point for read operations. You can read or fetch the data by asking for specific fields on objects using a post operation. So unlike REST, where we read using a HTTP GET verb, if you consume GraphQL or HTTP, you would be issuing a post HTTP normally to read data. And query operations start off with a query keyword, and you can give it an arbitrary name as well, although considered best practice. And what you get back from queries is hierarchical JSON that mirrors the query. This is a feature with GraphQL. You get response that mirrors the query. Going on to mutations. This is for mutating data or changing data, and is the top level entry point for write operations. Again, works over HTTP post. And then you have the mutation keyword used to write your queries, and mutations always accepts an input type as an argument. So in my case, it can be a user input type, which a mutation query can accept. Finally, subscriptions, which is a special operation that is very key or very unique to GraphQL. Subscription stands for pushed updates from the server. It's not polled by the client, but the server pushes updates to the clients, and clients can choose to listen rather than something being mandatory. It works over WebSockets and again uses an HTTP post. The keyword here is subscription. So the query starts with subscription, and subscriptions are stateful. So for example, a subscription would be, say, when a user is added or when a user is deleted. Suppose you want real-time information about something changing, then subscriptions can be helpful with GraphQL. And what type and fields would I have in my API? You would have the query, and I would have fields or the operations called users or user to read information about a collection of users or get to understand a single user. With mutations, I can have these particular fields or operations in my mutation operation type, which is create user, update user, and delete user. With subscriptions, I can have things like when a user is added, give me information, when the user is updated, giving me information, when the user is deleted, give me information, and fields corresponding to that. I have got a GitHub repo with a demo of code in it. I didn't choose to show it or live demo it today just because there's so much information to take in, but I have put the demo or the GitHub repo as a resource in my resource URL, which I will post on the Discord server later on. Looking at some queries. So if I want to get information about all the users, I can start off with the query keyword, give my operation an arbitrary name, say all users, and then I use the users field and ask for ID, name, and headline. Similarly, I can ask for a single user, starting off with the query keyword, followed by an arbitrary operation name, passing it the argument or the variable as an ID, and get the user who has that particular ID. I can add a user, giving a user input type. I can update a user. In both cases, it would get me back the information that has been added or updated. I can delete a user as well if I need. And finally, I can subscribe to pushed updates when a user is added, say, for example. And what about the pros and cons? With GraphQL, we have exact fetching. I get information that I ask for, nothing more, nothing less. There's again loose coupling between the client and the server, which means client and server can evolve at their own pace. We have auto-generating API documentation because of introspective feature of the GraphQL APIs or the GraphQL specification, and GraphQL is version free. But we do have caching complexities with GraphQL. We need to rely on something really custom because the queries keep on changing and it would not be easy to cache it. But I think Apollo has come with some ways and means of achieving this. File uploading, again, can be a bit tricky. With complex queries, performance can suffer a bit. Learning curve is kind of incomparable to gRPC and REST because GraphQL is a totally different concept in itself. And so if you are wishing to pick up GraphQL, be ready for the learning curve and of course the growing community. And finally, how do they compare? So the crux of my talk. So let's start off with the fundamental unit. With REST, it is resources. With GraphQL, it is query. With gRPC, it is functions or procedures. When it comes to the coupling between the client and server, it is low with REST and GraphQL, whereas with gRPC, there is very high coupling. The chattiness of the API, it is very high in REST, low with GraphQL, and medium with gRPC. The reason being gRPC still can get you all the information that comes back with the message. There is no way to pick and choose what you can get from a message. It's a fixed request, fixed response. While as with GraphQL, you ask for what you want and you get what you want. When it comes to caching, you have HTTP caching out of the box and REST uses that, while as with GraphQL and gRPC, I know you have to resort to custom methods, but I haven't really resolved that in my code. When it comes to discoverability, provided you have HATIOs, REST is good discoverability. GraphQL with auto-generating documentation, again, good discoverability. While as with gRPC, it suffers. You need documentation with gRPC. Versioning, gRPC and REST can need versioning. With GraphQL, you can go with no versioning. When it comes to performance, REST and gRPC excels, while as GraphQL can suffer on complex queries, but you can limit the amount of nesting that you can have on your GraphQL queries to kind of overcome that. Payload size can get heavy with REST. It's medium on GraphQL, depending upon the amount of data that you need, while as with gRPC, it is lightweight. The payload format, we'll keep it as JSON for REST because I think that's the most popular one. With GraphQL, again, it is JSON. With gRPC, it is binary. Browser support, REST and GraphQL is fine. But with gRPC, you need something like gRPC Web, which can actually convert HTTP one request to HTTP2 internally before the functions can be evoked because gRPC is built for HTTP2 and it's not really well supported by modern browsers yet. Standard or a spec, REST is only best practices, while as GraphQL and gRPC are formal specifications. When it comes to maturity, REST is really mature and has been widely adopted. With GraphQL and gRPC, it's still early days, even though RPC as a framework has been in existence since 1970s, if I'm correct. The learning curve is medium with REST and gRPC, whereas with GraphQL, yep, be ready for the learning curve. It takes a while to get your head around what GraphQL as a concept is. Learning resources, you would find a lot of resources with REST. Again, GraphQL and gRPC suffers on that. Finally, a bit of .NET goodness because I'm a .NET developer. REST has out-of-the-box support with .NET. gRPC has out-of-the-box first-class support with .NET. While as with GraphQL, we are reliant on third-party implementations. When it comes to Visual Studio support, we have out-of-the-box templates for REST and gRPC, while we are again reliant on external ones for GraphQL. And this is something that I wanted to cover off today, that is hosting on Azure. REST and GraphQL can be hosted on app services and Azure functions, but with gRPC APIs, app service does not support HTTP2 yet, as of I know. So you need to resort to something like Azure Kubernetes Service, or if you're using gRPC Web, that can be all means be hosted on an app service. And I'm not done yet because we have some bonus information for the day. So what are the tools that are available for you to test your APIs? With REST, you have Swagger UI or Swagger UI, which is now built in and part of the Visual Studio templates and part of .NET as well. We have Postman, and of course, you can use command line to test your APIs. GraphQL, when it comes to GraphQL, we have browser-based IDEs like GraphQL Playground. There's Insomnia, which I believe is a desktop IDE to test your GraphQL endpoints. We have Banana Cake Pop, which has both a desktop version as well as a browser-based version, again, which can be used to test your APIs. But these tools are much more than just testing tools. When it comes to gRPC, we have gRPC curl, which is command line to issue gRPC commands and test your API. Then we have gRPC UI, which can be integrated to your API, and that actually makes use of gRPC curl with a nice UI to test your API. There's Bloom RPC, which I believe is based off Postman as well, but I haven't personally used that or tried it out. And at the end of all of this, you have the client app, a console app you can build to test your APIs as well. But if you don't want to go to that extent, this is your way out. And some use cases. Where can we use REST, GraphQL, and gRPC? REST is best suited for management APIs where the focus is on objects or resources. We can have varied client, or where we have varied client usage, again, REST excels because all it takes is any client which can issue an HTTP request to consume a REST API. And REST can excel in microservices as well. GraphQL is the mobile API. GraphQL came into very existence because of the Facebook app. So it's made for mobile. And wherever the data is like a graph or relational, GraphQL excels. If you want to fetch data from multiple endpoints or APIs, again, GraphQL can act as like a gateway using schema stitching or schema federation to have a single endpoint to query multiple different APIs underneath it. And when it comes to gRPC, wherever you want action-oriented APIs, gRPC can excel. Whenever you want internal services, gRPC can excel. Note it's the tight client to server coupling that causes it. If you have microservices, again, gRPC can excel there. IoT devices, gRPC can assist there, and of course, polyglot environments. So that is it from me for the day. This is my resources for the day, which contains my GitHub repo as well, which I've put together. I will post this on the Discord server shortly. And thank you once again for having me as a speaker. I will be available on the Discord server later on for any questions. Thank you very much.